Okay, so welcome to our first talk in CE Seminar Virtual Series in the spring. My name is Lily. I am a professor in environmental engineering at Penn State. I have the honor to introduce our own Professor Bruce Logan today. He is someone who really don't need introduction, but I'm going to do it anyway. Let me look at my cheat sheet. So Professor Logan is an Evan Pugh University professor in engineering, the Stan and Flora Kappa Professor of Environmental Engineering, and director of the Eng Engineering, Energy, and Environmental Institute at Penn State. His current research efforts are mostly in renewable energy production and the development of energy sustainable water infrastructure. Dr. Logan has mentored over 130 graduate students and postdocs and hosted over 40 international visitors to his lab. He is the author or co-author of several books and over 500 refereed publications, and he has over 90,000 citations and H index of 148, highest number I ever seen. Okay, so he is well decorated, of course, you know. He is a member of the US National Academy of Engineering, a foreign member of the Chinese Academy of Engineering, a fellow of the American Association for the Advancement of Science, and the list goes really long, and I don't want to take the time from his talk, so I'm going to stop here, and the floor is all yours, or the Zoom is all yours. Okay, thank you, Bruce.
All right, well, thank you for that very nice introduction. Thanks for everybody being here today. I'm gonna talk about energy use and climate change, and specifically, I wanna get to talk about your own energy use. So I'm gonna give a few minutes of sort of motivation about climate change and why we should care, then talk about some of the challenges, like how much energy the US says we use versus what we use, a little bit about how we're going to look at energy use, and then I'll really try and focus on examples of energy use through what I call D&C units. And as we go along, I'm going to be asking a few questions just to make sure that we're communicating a little bit. So first one is, where's everybody from? We have nearly 200 people here. Where's everybody coming in from? Now, if you're watching a recording of this is being recorded. These polls will not show up. So I will try and summarize those. We have about 2/3 of the people are outside Penn State. So that's really good. I'm great to see the big community. And then for Penn State, about half students and faculty. So this is a graph that I hope many of you have seen. It's about CO2 emissions going into the future and trying to draw down CO2 emissions to be zero. But here's a couple things I want to point out. By 2050, that black line says we're not going to get there. We're only going to be at about half our emissions. So really, to get to really carbon neutral conditions, we need to have negative carbon solutions, which means we need sequestration. Now, I'm not really going to talk about that during this talk. It's mostly on energy. But I think we have to realize that we're not going to get to zero fossil fuel energy by 2050. We're just trying to get it way down so that eventually by, say, 2100, we can get there. And over the next 30 years, we're looking at about 1,000 gigatons of carbon. Now, nobody really knows what a gigaton is. It's a really abstract number. And I think also that it's difficult to even know energy results. So the next question I have for you is, how much energy do we use in the US? Let's start with that. If we're thinking about our own energy, what's the backdrop? And I really like this question because it's a little bit of a trick question, and I'll explain why in a minute. You got to be quick on your mouse too, because I cut it off after just about a few seconds here. All right, this is good enough to get so everybody says 101 quads, 101.2 quadrillion BTUs. And the trick part of this is that all three of these numbers here are all exactly the same thing. The correct answer is none of the above. Why is it none of the above? Well, if you actually look at what the US says we use, it's 102 quadrillion BTUs, which is 106 exajoules. But the fact is we actually only use about 96 quads, or about 100 exajoules. So why isn't the US telling the correct story? And if we zoom in on the renewable part of this energy, the primary energy, and we look at the energy going into electricity, a coal power plant is about 32% efficient, right? Primary energy into electricity. Natural gas is about 44% efficient, natural gas into electricity. What the US says is that for renewable energy, we're going to use a primary energy of an efficiency of 37.5%, which means primary energy, they're saying, is 1.04 quadrillion BTUs to produce 0.39 quads of electricity. But that's a made up number. Actually, solar panels are about 20% efficient. Hydroelectric plants are about close to 90% efficient. These are made up numbers. And so the implication of this is when the US says for our electricity infrastructure that we're using 39 exajoules of primary energy, that's wrong. We're actually using 35 exajoules of non-renewable electricity to produce our 14.2 exajoules of electricity. Now, to put that again against the backdrop, it's about 100 exajoules of total energy consumption. So exajoules, quadrillion BTUs, these are all lots of different units, but your daily life is dominated by other sorts of units. And so, how many miles per gallon does your car get? Well, you probably know that. But what about how many kilowatt hours your house gets? So how many of you know about how many kilowatt hours your house uses in a day, or what the national average is for a house in the US in terms of its electricity use? And good, we'll stop it there. It looks like we've got a consensus that it's about 60 kilowatt hours per month. And actually, the answer is 30 kilowatt hours per month. So, the problem with energy is it's all in different units. And like languages, when we want to talk to each other, what we do is we agree on a common language, or we translate it into something we know. So I either speak the same language or we have a translator. Same thing with energy units. We have to learn to take these disparate units, where calories with a capital C is different than calories with a lowercase c, and translate it into something we know, maybe kilowatt hours or BTUs or something like that. So look at these different energy consumptions, how much food you eat, or your house, or things like that. We could, for example, convert all these into a kilowatt hour. But I don't really think we have a sense of what a kilowatt hour really means relative to all these numbers. So, what I'd like to say is we ought to relate it to something we know. And so let's start with something we know, which is everybody needs to eat about 2,000 calories a day. And let's relate that to something else we might know, which is how much electricity we use. Let's go to the next poll. So if we were to power light bulbs off of 2,000 calories a day, how many light bulbs could we light up continuously that are 100 watts? And if you've heard any of my talks on energy before, you hopefully know the answer to this question. Okay, that's a pretty good range. I think it's pretty typical here that most people guess about 5 to 10 light bulbs. And here we have about a third of the people said 10 100-watt light bulbs. And the answer is one light bulb. Actually, we only need 2,000 calories. You translate that into watts, and that's about 97 watts, or about 100 watts. So that tells you that we sort of have this disconnect about how much energy we think is in the food we eat and how much energy we're using. Now, the other side of the energy climate change nexus is when we eat those 2,000 calories, how much CO2 is being emitted into the environment from that food we ate? Just from the 2,000 calories, the beef, the hamburger, or whatever we ate, how much of that was, how much CO2 do you emit as a person? So in pounds per day, because you ate breakfast, lunch, and dinner, how much net CO2 do you emit into the environment? And I gave you an out on this one, as in, yeah, I don't have a clue. You can guess, or you can go with that. That's up to you. Well, I don't have a clue people have won it. The next best guess was about a half a pound of CO2, and the actual result is 2. So you emit about 2 pounds per day of CO2. And what I'm going to say is that I'm going to call this 2,000 calories one daily energy unit. I'm going to call this 2 pounds a day of CO2 one daily carbon unit. And so we can look at our activities on this basis. And let's guess now, how many trees would I need to take that 1 C of carbon out of the environment? Now, the carbon in the food I ate is carbon neutral, but it's just a question of how many trees are needed to capture 2 pounds per day, or 1 C of carbon. I guess, this will also be how many trees should you have in your property to take up all the CO2 of all your activities, would be one way to look at it. And so the winner seems to be about 1 tree, and the answer is 15 trees. So we need about 15 trees to capture just that 1 D going to 1 C of energy. And so this is kind of the perspective I'm taking, is let's look at everything on the basis of how much water do I need every day? It's about 1 gallon or 4 liters. How much energy do I need? Well, 2,000 calories just to keep me going. And then 2 pounds a day of CO2 coming out. And when you now look at some things like home for your energy for your home, it's about 13 times that energy that runs you. It's a gallon of gasoline actually has 15 D, so a little bit more than even the energy that it takes to run the average home. Food to your table, about 24 D. Again, 100 D, not again, but 100 D for the energy that everybody in the US uses. You take all the energy we use, that 100 exajoules, divide by the number of people, and you get about 101 D. Now, there's a curious conversion here that we use about 100 quads, about 100 exajoules, rough numbers, but the exajoules for everybody in the US works out to be almost the exact same number as D. So whenever you see D, if you want to think, oh, that's exajoules for everybody in the US, or put it into some different units, that's how you do it. 1D is also about 2.3 kilowatt hours. So whether you want to use D or you prefer kilowatt hours or exajoules, that's what you can go for. We have the 100 D or 100 exajoules of all the energy we consume. About 2/3 of that is not related to the electricity infrastructure. It's related to other things. And most of that is petrol products, oil and gas and that sort of thing. But I'm not going to talk about that so much from the perspective of petrol. I want to talk about trying to think about decarbonizing everything, going to a green electrical infrastructure. And so if you look at what we have now, this on the left, this 35 exajoules or 35D, and you look at the renewable energy part in terms of primary energy, where that renewable energy is just the electricity on the left, and then you convert that into electricity energy on the right, you can see that renewable part starts to get bigger, right? Because we're just looking at electricity in both cases. And in fact, as we transition from fossil fuels into electricity, we're going to use less and less, quote, primary energy because it's going to be renewable and we're not going to be consuming that primary energy. So we can shrink and watch our energy use go down just because we're shifting to renewable energy. So let's shift now to talking about our own lives, our house, our cars, decisions that we make in our life. So for example, the electricity in your house is about 13D, powered by the US electrical grid. That's about 5C, okay, just in terms of the fossil fuel footprint of that electricity. And if you have 2.51 people on average in a home, that's really about 5D per person. Now the question is whether you include natural gas in that. A lot of houses in Pennsylvania have natural gas heating and electricity as well. And in Pennsylvania, if the average house uses about 20D of natural gas to heat the home. So one of the things you think about here is, should I use natural gas to heat my home, or should I use electricity? And the answer is, it depends. Now it's a complicated table, but the purpose of the table is to get all the way to the right for the things all the way on the left. How much carbon do I emit from natural gas for heating a typical home? And if you're using natural gas, it's about 8 or 9C. That would be, times 2 pounds per day of CO2. If you have a heat pump, you get down to about 5C for the most efficient heat pumps. How can heat pumps be more efficient than natural gas if the natural gas is 95% fuel into heat? The answer is that a heat pump moves heat. It doesn't heat up itself. And so it's like if you carry groceries into the house and you're carrying 2,000 calories of groceries into the house, it didn't take you 2,000 calories to carry those groceries in the house. So the first thing is the efficiencies of heat pump are above 100% relative to how much heat they can move or how much air conditioning they can provide relative to the energy that's needed to run them. So you can make a big decision in your life to simply, when you have a home or you need to retrofit a home or you need to build a new home, to make sure that you use a heat pump whenever possible. Now, if you have a heat pump, you don't need that natural gas. You can use electricity. If you take the average solar panel sold today, which produces about 320 watts under full illumination, and can do all the conversions, it's about 0.6D. So if your house is running on 13D and your solar panel is 0.6D, then you need about 23 panels. If you want to run your car off your solar panels and you're driving 37 miles a day, that's about another 4D or about another 7 panels. So for 30 panels, you could power the average home and car, and essentially have a neutral footprint. I have a personal interest in this. This is my house. I put solar panels on it. You can see before and after on the upper right and then the bottom. And being an engineer, of course, I tried to figure out how many I needed and how well, what they were telling me was going to happen would happen. You can see the energy in the blue and the gray. That's how much energy and electricity we used in each of these months in 2019 and 2020. So there's a lot of variability in that. And then you can see what they estimated in orange versus what we produced in green right next to each other. And you know, they're pretty close. This July was absolutely the hottest, sunniest month on record. So I did a lot of great solar energy production, but of course air conditioning was turned on, which kind of negated it. But the point was they can predict it pretty well. And the other thing you have to know is, you know, how long does it take to pay back for solar energy? Now, my contractor gave me some numbers, and I translated that into 15D. In 2020, my panels produced 17D. So I'm pretty much on target for what they say about what you should be able to do. And if you look at different states and what electricity is selling for and the federal discounts, you get tax credits for this, your solar panel should pay back in about 10 to 12 years, depending on where you are. And if you look, interestingly, Maine and Arizona, the payback is almost the same because electricity is cheap in Arizona. It's really expensive in Maine. Maine doesn't have so much sunlight. Arizona's got a lot of sunlight. So the payback ends up being about 10 years pretty much most places in the country. But you're probably using a lot more electricity in Arizona for cooling, so you should get them. All right, what about cars? I got another question for you on this one. And the question is, what car emits more CO2? A Toyota Prius hybrid that gets 52 miles per gallon, or a Tesla Model S, which is the energy efficient one, being powered using electricity from a coal-fired power plant? Now, you might want to think, well, this must be a trick question. Of course, the electric car will produce, will have less net CO2. Let's see here. You see about 2/3 of you said the electric car and 1/3 the Prius, and actually that's right. Let's take a look at why that is. I should first tell you, for those of you who may not be in the U.S., we use MPG here, of course, in the U.S., and it's liters per 100 kilometer. The little quick thing is 234 divided by MPG, or 234 divided by liters per 100 kilometer can interconvert those units. The way we evaluate electric cars is with this miles per gallon E. That's how much energy, electricity energy, a vehicle uses that's in a gallon of gas. So if you look at the miles per gallon of 3 cars, an average car, which sold here, gets about 25 miles per gallon, a Prius, which gets about twice that, and a Tesla 3, in terms of the energy they use. And now the Tesla 3 converted back to primary energy. So it's the energy that went into making the electricity that got to your house that powered this. It's not a coal plant, it's the US grid on average. The Prius actually uses a little bit less energy, primary energy, to go the 37 miles. However, when you look at the carbon emissions, because the primary energy for the Prius is gasoline, the primary energy for the electricity produced is actually a range of things, some of which is carbon-free, nuclear, and renewables. It actually emits less carbon. So if you run the Tesla on the US electricity grid, it has less carbon emissions. I'll get back to this 141 in a second. I'll get to it right here. There's that 141, but if you convert that now to what I have, this capital E here is the primary energy, that Tesla is getting about 45 miles per gallon, which is why it's using more energy. But if you look at the carbon emissions now, so this is an average car, the Prius and the Tesla. If you're on the US grid, it's about 5C. versus 7C for the gasoline for the Prius. But because coal is produced very inefficiently, electricity efficiency is like 33%, and it has a lot more carbon emissions than gasoline. That Tesla, if it's running on a coal-fired power plant, is about 12C versus 5C on the US grid, or 7C for the Prius. 141, what is 141 miles per gallon equivalent? Again, that's energy in 1 gallon of gasoline. I thought you might find it interesting that you the human being, you get about 300 miles per gallon of energy equivalents. That is, you could walk 300 miles on the same amount of energy in a gallon of gasoline. If you bike, you can go about 600 miles. If you use these little electric scooters, actually, you can go almost as far on the same amount of energy. They're pretty efficient, but they're not safe at all. So don't use them. They're really, really a bad idea. And this guy, of course, I show you in the picture, doesn't have a helmet on. Sometimes people ask me about hydrogen. I do a lot of work in hydrogen. So the question is, why not hydrogen for these vehicles? Well, the study that California is doing is saying that light duty vehicles, that is like cars like you're seeing here, are not really anticipated to be fueled by hydrogen. It's a nice idea. It's not that it's not energy efficient, but the real need for hydrogen is in heavy duty vehicles, that is trucks and larger vehicles as well. In fact, people are talking about using hydrogen or ammonia for large shipping, or for hydrogen for airplanes. This is something by Airbus. And so people are looking at green hydrogen as being a source of wind or solar being used to split water and make hydrogen as a very sustainable way to power those vehicles. And the biggest hydrogen project being planned in the world right now is a $5 billion plant that's under consideration for construction in Saudi Arabia. And they would make hydrogen, turn that into ammonia, transport it, and then turn it back into hydrogen. Of course, maybe they just use the ammonia that they have. So I've told you now what you can do with your house. I've told you what you can do with your car. And let's get back to that question of food then. How much primary energy, so that's the energy in the fuels to get the fuel, the power of the harvesters, the energy in the electricity converted back to primary energy. How much energy does it take in units of D to put that on your table when you are going to eat 1 D of food? This is also a little bit of a quiz of how much you've been paying attention, because I told you this number earlier on, so that'll be interesting. But I'm throwing a lot of numbers around, so I don't really expect everybody to get this. So the answer is 13D of, by consensus, about 50% people said 13D. The answer was about 25D. So the food system, and you can read this, it's published widely, about 13D, and getting back into exajoules, or about quadrillion BTUs. It's energy to produce the ammonia that goes into the fertilizer. It's energy that goes into transportation and all these other things. It's about 13D, but the reason the answer is 25D is because it's primary energy. When you take this energy makeup for the food system, about over half of it is for electricity energy. But of course, you have to make that electricity somehow. So when you go and look at the US grid, convert that back to primary energy, it's about 25D. And this lower little donut here says, of the 25D, where's the fossil fuel energy coming from? And it's basically a lot of natural gas, but a lot of coal now because of the connection to the electricity. Again, about 100 D for the whole thing. So 25, a quarter of the primary energy being used in the US is for the food system, which is not something you can directly control like you can your house or your car or something like that. That results in about 11 C of carbon emissions. So 1 C that you breathe out due to eating the food is about 11 C. And because we're in America, we eat a lot of hamburgers. I thought I'd throw hamburgers up here, or I should say burgers, because a quarter pound of burger is about 6 C, 11 C, 6 C. And if you decide to go for some of these Impossible Burgers, Beyond Burgers, vegetarian burgers, that new wave of burgers, you can get that down to about a half a C, which is pretty good. And also the water use drops way, way off as well. So I encourage you to try the Impossible Burger. They're really good. I mentioned ammonia and the amount of ammonia going into making, the amount of hydrogen that goes into ammonia into fertilizer. About half the hydrogen made today goes into just making ammonia so that we can get modern agriculture. And that is about 1 to 2% of all global CO2 emissions is due just to making hydrogen. So let's bring it down. Let's bring it back down then to, you know, what you have control over and sort of the things you don't. Because I think a lot of the people tuned in are thinking, okay, you know, 100 exajoules, what can I do about that? Let's just think about these things I've mentioned, sort of your food energy, your house, maybe some natural gas to heat the house, gasoline, and travel, one international trip or a couple domestic trips a year on an airplane. Where does that put you? Well, that puts you at a total of about 68 D, with about 57 of that D coming from fossil fuels. So these are the things that you control, right? You got to eat, okay? Everybody has to eat. Then you convert that back to primary energy. You consume electricity for your home, natural gas, and vacation and gasoline. You can see that. Look how big that gasoline piece of the pie is. It's pretty big. That shows you how important, you know, that 1.2 gallons per day that we use on average in the US. And the food system here, this food from fossil fuels directly, and then the fossil fuels that we're used to make the electricity, that's a big part of it too. It's about, you know, a third of that. So your activities and your food, about 30 C. Going back to trees, if you wanted to balance off that 30 C of emissions, you'd need about 450 trees. And just to let you know, an acre typically has about 100 trees, maybe a couple hundred in a well-managed area. So unless you've got a lot of land, you're not going to make it, but we do have a lot of land in the US, so there is some hope there. That 30 C that I'm talking about from those activities I described can be compared to the 50 C on average for the US. And so when you look at these two numbers, what I'd like you to think is, you know, that 30 C, I actually control a lot of that. I control it based on what I drive, how my house runs, and what I eat. And so let's say that you took that 30 C and you put solar panels on your house, and now you're fully solar, powers your car and your home and your heating and everything else. Now you're down to about 15 C, because that's what's in the food infrastructure, and you can't really control that. Where do we want to get to? This is getting back to this question of global CO2 emissions. Well, we want to get to, you know, optimally, we don't want any C to come out from fossil fuels. There's a society called the 2000 Watt Society. I'll call them the 20D Society, who suggests maybe 15D of renewable and 5D of fossil fuels. If we're looking at 5D of fossil fuels, that's about 3C. So we're looking as a goal maybe to try and live a lifestyle that's 5D and 3C. Wow, I mean, that is a pretty tall order because we're at 100D and 50C in the US. The scenario I went through is like 60 or 70D versus 30C. In Switzerland, where the society originated, it was about 50D. I don't know what their C was. The world averages, all the people in the world, all the energy used in the world, 25D, 12C. Okay, so we're on a path of climate change, which is really bad just based on the world having 12C. Now, I'll look at this a little bit complicated, but this sort of breaks it out into the world a little bit more. Look at the two bars here for the USA. This beige, blue, and green one, that says, where is our electricity primary energy coming from? You know, what are our sources what are our sources for the energy? So, you know, you've got the beige is renewable, is fossil, the green is nuclear, and the blue is nuclear, and the green is renewable. So, okay, you know, so there's our fossil fuels and our non-carbon ones in color. Of the fossil, we have about half coal, half natural gas. You can look in, say, the Middle East, you know, where it's about half oil and half natural gas, or you can look at China, where it's almost completely, the fossil fuels are almost completely coal, and they have a mix here of renewables and carbon-free as well. So a couple things to see from this. Well, you know, the carbon content of this coal is just awful. The energy efficiency into electricity is awful. We want to get away from that. Everybody wants to get away from that. We all want to take this balance and shift it to the color, the blues and the greens, away from this beige color. The other thing is that the electricity use in the US is about twice what it is in China. The fossil fuel footprint is much greater in China overall because just a large number of people. But when you look at normalized to the number of people in China, it's actually about half what it is in the US. So again, getting back to the US, you have a lot of control over carbon emissions and energy use because, well, frankly, our energy use is so high. Okay, I'll just say something really quickly too. We're in a civil engineering department here. You know, the main three things that probably we need to think about are transportation, that's part of civil engineering, and our infrastructure in terms of concrete and steel. Concrete and steel are responsible for about 13% of global CO2 emissions. And so we can certainly solve our personal lives by what we, you know, the buildings we choose to live in, but modern cities have moved beyond stone and a little bit of cement into concrete and steel. So that's something we need to think about. Globally, the carbon emissions are going way up because of the rapid growth in concrete structures in China primarily. It's going up. If you look at the world minus China, that's the gray line. It's going up without China, but it's more in proportion to population. And so, you know, this isn't a blame China thing. China wants to be industrialized like everybody else. But the problem we all face is that when you make cement and you take calcium carbonate, you release one CO2, and that's the stoichiometric relationship you cannot change. And so if you're going to use Portland cement, if you're going to use cement to make concrete, you're going to have these CO2 emissions. And so for the civil engineers, and I know there are people in the department that work on this, like Shad, you know, we need to look at these alternatives that we can't make impact CO2 emissions significantly unless we find alternatives for Portland cement. That's the way we do it. And there are companies working on that. And as civil engineers, we need to embrace that and find ways to use that. And so I'll finish up now on the last topic, which, you know, I've been working on sort of as we go through this concept of, okay, let's reduce our energy, but we're not going to be able to reduce it all. We need to think about climate change and carbon capture and sequestration. It can be tied in with energy, as I'll argue, but we need to recognize it has to be a part of our energy infrastructure. It has to be intertwined with our energy infrastructure. Trees are great. As I said, 15 trees will get you 1 C. And so if you got 20 C, you know, you do the math. You can shade your house. That's good for reducing air conditioning. One of the concerns with trying to solve carbon capture through natural solutions like trees is that if there are wildfires or pests, then you're going to lose that carbon right back up into the atmosphere, which has certainly been a problem in Australia and California in this past year. You know, not just above ground, but also below ground, there's a lot of carbon in soils, and about 500 gigatons of carbon CO2 equivalent has been released from soil due to agricultural practices. 500 gigatons. We're talking about 1,000 gigatons that we need to avoid and get out of the atmosphere, and 500 came because of the loss of soil carbon. So when you put a tree, you're not just getting the carbon you see above the ground, you're also getting the carbon capture into the soil. So to think about climate solutions where you capture carbon into trees and soils, that's great, but we still need energy. And so a recent study by Tom Richard and Erica Smithwick here at Penn State and some others said, well, look, if we have this land that we're currently using and we were to grow, say, switchgrass, which we could make into biofuels, we could gain a lot of carbon sequestration into the soil because these plants have an immense root system. And we could use that above ground carbon as a way to make biofuels. And if we link it to carbon sequestration, injecting it into the ground, we get another benefit. And so this is a great paper. I won't go into it to say that, you know, by thinking about dual use, where we get both biofuels, liquid biofuels, as well as carbon capture, that's a win-win situation. Another thing you might think is, well, let's take that miscanthus and let's make electricity out of it. Let's take it as a source of energy. We'll grow the biofuel, we'll convert it in a power plant into electricity, and we'll use that electricity. But let's think about using an acre as to grow miscanthus, which is the best possible fuel you could have, versus, say, putting solar panels on that acre. You'd be looking at 33D of energy if you use the biofuel as electricity versus 100 times that, about 3,300 D if you put solar panels on that 1 acre. And that's why solar farms are really important. Even if, you know, we can put some solar panels on our house, but we need to turn a lot of acreage also into solar farms. That's how we're going to make the energy that we need. That's how we're going to make the electricity that can be carbon neutral. Another consideration might be, okay, well, you know, aren't I better off maybe, say, capturing this carbon into trees? And of course, if I do that, I can't put up solar panels. Well, an acre of trees is going to draw down about 6 C of carbon. But if you put an acre of solar panels out there, you're avoiding about 2,000 C if you were to make that electricity as we do in the US grid. So, you know, at least in terms of drawdown solutions, where we can put trees, let's put trees, but if we can put solar panels in places and generate electricity like that, it's going to avoid a lot more carbon than it's going to capture. I think we're all going to see in the coming months with the new administration a real emphasis on carbon capture. Right now it's too expensive. This is just the capture part, 200 to 700 per ton. There's a group led by David Keith, I think is his name, for building these huge fans to move air through these fans and capture CO2, and then you still got to inject it. The cost there is lower, getting into around $100 per ton, which is supposed to be a good range. I mentioned one though that again is an integrated solution in Belgium, in this town Mol, Belgium. They have a geothermal energy, and because of the geothermal energy, they have a lot of fans and blowers. And so they think, well, you know, if we could integrate carbon capture into these blowers, which are already blowing, we could probably do this for about $70 a ton of CO2. So there's another good example of trying to think about things you have to keep running just for geothermal energy, which is a renewable energy source, as well as dealing with carbon capture. So fully to come back around, we're looking at about 30 years. We need about 1,000 gigatons, 30 years at about 30 to 40 gigatons per year. We got to pull that down. How are we going to get to this 15C globally to 3C based on the 2,000 watt society? Project Drawdown has a lot of solutions for that, but Project Drawdown requires Project Us, all of us, to think about what we can do for that drawdown. And there's a lot of control that we have in terms of you know, how we buy, purchase green electricity, or make it on our homes, or put in solar farms, as well as what we eat. So I started out with this graph. The one on the left is the one I showed you at the beginning. The one on the right emphasizes if we don't get that black line, you know, if things keep going up, we're at 4 degrees C or 5 degrees C. You know, those are also global averages. And land temperatures tend to be almost up to twice as hot as global averages. So, you know, you're looking at 5 degrees C, you're looking at 10 degrees C and like 15, 18 degrees Fahrenheit. I don't think that's the future we want. And I hope that at least this talk, I've convinced you that you actually have a lot of control over this. You can choose what you drive. You can choose to use heat pumps in your house, or electric baseboard heating, or, you know, many decisions in your life. Take control of that and try and do the best you can, and communicate that to others, that we do have these things that we can make positive decisions about. As a country, we need to work on our food system. We need to rethink how we transport, grow, make ammonia, and do all these things that can will definitely have a huge impact on our overall carbon emissions and energy use. Natural carbon solutions are going to be there. Trees do work, there's no question about it. But ultimately, to get down to the 3C, we're going to need both carbon capture and sequestration. So I will stop there, and I'll leave the slide up for just a minute there, and turn it back to Lili for questions and comments if we have time. Thank you.
Thank you, Bruce. Okay, so for the question session, I think we will feel free to unmute yourself to ask question directly. And if you're more comfortable, you know, typing question in the chat, feel free to do that too. And I will alternate between, you know, the whoever asks directly to questions in the chat. I'll read it out too. Okay, go ahead.
I think there's plenty of questions and plenty of comments in the chat, but if you could work through those, I was obviously not able to follow that.
There are no questions. They're mostly comments.
Mostly comments. Okay.
Yeah. Yeah.
I've got one, Bruce. This is Andres. So thank you for that. That was a great talk. I think you distilled a lot of what I want my students to take away from my class. So maybe I'll just show this at the beginning of the semester, and then, you know, go make myself a good drink and call it a day. So thank you for that. No, you know, the first time we talked about this idea of D and C, it was like in its infancy a couple of years ago, and it's good to see how far it's come. I've always been kind of resistant to the idea of framing these issues as a personal choice, because I think that these are systemic problems, but I think that you've done a really good job explaining why this helps raise awareness that can then lead to support for systemic change. I guess my question is about marginal cost of D and C, and whether you've explored that, because at some point, you know, the the benefit of me making some of these choices, you know, my money would be better spent doing other things. And, you know, sometimes with these conversations we're preaching to the choir, and given that we're all in this together, and that, you know, in Charlottesville where I live, for example, there are neighborhoods where people live in trailers that pay $500 a month to condition a space that's far smaller than my house. I wonder, you know, if you've gotten to the point where you're starting to look at this idea of sort of marginal cost of D and C.
No, you know, it's a really good point, and a lot of people, you know, approach this from sort of the economics of what's this going to cost, and what, you know, what can we do, and they'll say, use the example of the heat pump. These high efficiency heat pumps are not cheap. You want to retrofit your house, throw out your existing system and pull in a new one, it could be $15,000, and you'd say, that's a lot of money. But the question is, can you find an opportune time to do that? Like your old unit just gave up, so you replace it with a new one, and you know when you go to do that, that's the right thing to do. But my point with the solar panels was that actually those panels are pretty cheap. In 10 years, they pay back for themselves, and they're going to last. They're warranted for 25 years. I know the inverters and there's other things, but they're warranted for 25 years, and they're expected to last 30, 40. That warranty could even go to 50 years in the next generation of panels. So the person living in the trailer, they can't afford that. They're never going to be able to do that. But the town makes a commitment to, you know, work out land deals and buy solar power from vendors and storage, and next thing you know, the whole town's running on electricity. So, you know, I think there are things that when you raise awareness enough, people that have control over certain things can make decisions that will help you. But the early adopters will be the people that can afford the Tesla and the Prius and the, you know, the better systems.
Great,
Thank you.
thank you. I have a question from the chat from Laura Chavez. Hope I pronounced your name right. Question, does your comparison of land use for trees versus solar panels take into account the manufacturing cost, energy versus carbon for the panels?
Yeah, that's sort of like the life cycle analysis on it. And it's a really good point. You know, there's a lot that goes into that overall evaluation. I think the overall carbon footprint for a solar panel is very low. I don't remember what the number is, but because it lasts 25 years or more, the amount of energy that went into making that panel is very small. It's like the energy that goes into making a road. You know, you can make that road, and if you calculate, you know, the energy based on, you know, the using it for 6 months, it's a lot of energy. But that road lasts 20, 30, 40, 50 years, then the amount of energy per day, per mile is a lot lower. So, you know, I don't think the solar panel carbon footprint is that high.
Okay. Feel free to jump in. If I don't hear questions, I will read from the chat. There are questions from the chat. Okay, another question from Noel Habashi. Can Bruce please clarify, does electric baseboard heating produce fewer Ds and Cs than natural gas heating?
Yeah, that's a, you know, it's a good question. I can go back to my slide on this. You know, the thing about the electric baseboard heating is that it's very efficient for heating, right? Because the electricity that comes in, it all goes out as electricity. But the problem that you have is that that electricity had to be made. And so if you look at the columns there, sorry, I got to move my thing around. If you look at the, oh, that's the car, sorry. There we go. If you look at the the electric, this is electric in the middle, that's the baseboard heating. And that electricity from the US grid comes out with a C of 17. If you look at natural gas, it's about half that. And if you look at a heat pump, it can be about the same or up to half that again. So again, the baseboard heating is just turning that electricity into heat. But you had to use a fuel to make that electricity. Then you lose about 7% of that electricity to get it to your home. And then you turn on that heater. So it's really, it's the most expensive way. And well, it's the most carbon impactful way to heat your home. In terms of somebody building a house, it's very cheap to put in electric baseboard heating, getting back to the point, you know, about the capital cost. Electric baseboard heaters are really cheap, but you're going to pay a lot every time you turn them on. So from a carbon point of view, they're terrible.
Okay, I see a raising hand from the audience. Juliet, Oman,
Yeah.
Neomo. Yeah.
Okay. Great presentation, Bruce. I have a question with respect to the food aspect of the analysis. So my background is anaerobic co-digestion. So I look at food waste and wastewater sludge and how to improve energy recovery in that line. So I was curious to know if in your analysis you took into account the fact that within the food production chain, the amount of waste, food waste that is in there, and how that also contributes to the sea. And if we were to put that amount of food waste to a good use, for example, through co-digestion, how do you think that that is going to impact the analysis?
Yeah, it's a really good point. And I don't have time to cover it all, but you know, food waste, maybe, I'm trying to remember the number. It's like a third of the food is wasted in the US. So just take that 24D that goes into the food system, you can change it to 16 essentially by just not wasting food. And then if you were to take the food that was wasted and put it into anaerobic digestion and then get back a certain number of D from that, that could go into the electricity grid or be used, you know, as a fuel as well. So I don't think you really want to intentionally grow food and have to put it into a digester. But if your choice is to throw it in a landfill or throw it in a digester and actually capture the gas and use it, you'd be much better off putting it in a digester. And we just don't do enough of that. The waste that goes, you know, anaerobic digesters at wastewater treatment plants are really making methane out of energy that started out as food as well. So, you know, we do it from that perspective, but again, not enough.
Yeah.
Okay, I don't see other raising hand. I'm going to read from the chat. Next question from Erica Luago. If there was just one thing a person could easily do to lower their CO2 emission, what would you suggest it be?
Walk, don't drive. The gasoline use, because the gasoline use, 1 gallon of gas is about the same amount of energy as your whole home. So if you burn a gallon of gasoline, it's like a house full of energy you've just wasted for that day. So that would be the number one thing, is walk. The second, you know, oh, I can't do the second thing, but just analogously, don't take the plane ride to, you know, halfway around the world, which I have to say I'm doing pretty good this year on.
It also have health benefit too, walking, right? So
Absolutely.
it's win-win, yeah. I see another hand from Rahman Azari.
Hello, yes, Ramon Azari. I'm an architecture faculty. Thank you very much for a great presentation. A lot of what you mentioned can be used in my course as well. So I'm going to probably use your lecture and video in my classes as
Well,
well.
I should say, Raman, before you ask a question, anybody that wants these slides, I have them also in a format. You know, I have a much more extensive version of this. Happy to share all those with you. Go ahead.
Thank you very much. In buildings, we have learned how to reduce and minimize the operational energy consumption of buildings. We have gotten to the point that we are able to design and build net zero energy buildings, net zero water, net zero waste buildings. Recently, there is a trend to even reduce the embodied energy and carbon of the buildings. There is also the efforts to use glue-lam timber and cross-laminated timber in high-rise, mid-rise, and high-rise buildings as well. So that would ideally reduce the embodied carbon of the buildings. The concept of carbon capturing that you mentioned in one of the slides was very interesting to me. What do you see as potentials of integrating carbon capturing technologies into buildings? What I saw in your slide, I think, was at larger scale rather than building. Do you think it would be applicable to the building scale?
Well, that's probably a question for more of an expert on concrete and cement. You know, some of these products have claims of being able to absorb CO2, net absorb CO2 into the structure over time. I've been told that that is really not proven. I think it's a really big challenge. I don't know that buildings can be carbon absorbers in any way, but certainly a great reduction through complete recycling of steel will have a huge impact. Steel is something that can be very easily recycled for, you know, the same purpose it was being used for. Concrete can be used, at least in terms of the material as an aggregate in making new concrete. But fundamentally, we have to make cement and concrete materials differently than we do now. And that's where it'll have the biggest impact, is not emitting that CO2 and making it.
Thank you very much.
You're welcome.
Okay, I will read one question from chat and then go back to raising hand. Question from Gina Ellis. Any thoughts on indoor agriculture, vertical farming? I think this will reduce carbon emission.
I'll be honest with you, I haven't really, I know what you're referring to. I haven't really thought about it, but it seems to me if you're going to do something in a building, that it couldn't be as carbon neutral as it could be outside. But I haven't really read anything about that. I don't know. And actually, if you have, who asked the question, you know, let me know. But I don't know the answer to that one. It's a good question. I have no idea how efficient or any energy efficient or not efficient. I would hope if you're doing anything indoors, though, that it's powered by solar panels and stored electricity.
Okay, Hannah Array, raising hand.
Hi, I just had a question, and you might honestly not know entirely about this, but what is your opinion on like lead development? I've heard mixed opinions from different people, just thinking, you know, if it's actually worth it, if it makes a difference, or if it's just, you know, a lot more effort than what it's worth.
I'm sorry, on what development?
Lead development.
Lead.
It's like I guess a green
Like a green
infrastructure
LEED
building.
certification?
Yeah, like that.
Oh, yeah, LEED certification is, I mean, it's not something that, you know, I've worked on extensively, but this is to really work on addressing the energy that goes into not only operating that building, but putting that building together. So these different LEED certification levels are I think, really important when you're considering building a building, and it's at a direct effort to try and lessen the CO2 footprint of our building. So I think it's a great thing. I don't know how far it goes, but LEED certified is better than non-LEED certified.
Thank you.
Sure.
Okay, before I read the next question, just so everyone knows, this is recorded and the video will be on CEE event. And also, if I can figure out the way, I will email everyone the link or everyone who registered. Okay. Next question from Lindsay Pollard. Thinking about community level decisions, do you have any idea what the impact of replacing a grass athletic field with artificial turf means in terms of C?
So in terms of replacing what?
Replacing a grass athletic field with artificial turf.
Well, it doesn't sound like a good thing to do. And once you're at artificial turf, then you're stopping that potential for carbon sequestration into the soil. Again, getting back to my point that we've lost almost 500 gigatons of carbon out of the soil. We can't put all that back, but we can try and put some of it back. But we need plants to grow and to grow root systems down into the ground so that they can transport carbon from the atmosphere into the soil. And then even as it decays in the soil, it will leave some of that carbon there. So it's really important to have plants that have a lot of extensive root systems under the ground.
Okay, cool. Next question. There's a lot of questions in the chat, so I'm just going to keep shooting you.
Well, I know an hour and a half is pretty long, so maybe another few minutes, and we can let people go early. How about that?
Okay. Yes.
And they can all feel free to email me and contact me later if you'd like. Go ahead.
Okay. Whenever you feel like we're done, we can wrap up. Next question from Michael Sauzen. Would increased transition to renewable lead to increased, would increased transition to renewables lead to increased energy consumption and result in a forced mindset?
Yeah, that's a good point. I often say that one of the nice things about having solar panels on my house is I don't worry too much in the summer about running the air conditioning as much as I used to. So I think there could be a little bit of that, quite honestly, that you're like, woohoo, it's carbon neutral now. But electricity costs money and people want to save money. So I hope that they, from that perspective, it wouldn't increase. The renewable energy is still, it's whether it was what you pay for the solar panel or what you're paying for the renewable energy, it's still a cost. But a couple of good things though, light bulbs, we don't use those 100-watt light bulbs anymore. We use 10-watt light bulbs. Refrigerators now use about half the energy they did 20 or 30 years ago. TVs, these high efficiency LCD and flat panel screens use a lot less electricity than the old CRT, whatever, cathode ray tubes, whatever they are. So, the technology has also moved to save more and more energy, and everybody wants their phone to go longer on a charge. So I'm hoping all these changes will actually reduce energy consumption, and our desire to not use that electricity or energy will be reinforced by our desire to avoid climate change and save money.
Cool. A question from a student on campus, Tyler Berry. Being a college student who doesn't use a car, how much carbon emissions do the Kata buses emit when we ride them to and from campus?
So it's called ride sharing, and it really depends on how full the bus is. So right now, all the CATA buses running around State College are not doing a very good job of, but I will also tell you that Uber and Lyft and these sorts of ride sharing are really terrible in terms of carbon emissions because they idle a lot, they run around from location to location, they end up driving a lot more miles. So, you know, using a personal car that gets above 25 miles per gallon is actually a better thing to do than to, you know, Uber around all the time because it's a lot of carbon. So, you know, a lot goes into that. How often do you use the car? How far do you drive and things like that? But if you're a college student, you're probably going on buses or walking or biking or using Uber. And if you've had a few drinks downtown, I would say take Uber or take the bus. I wouldn't, you know, it's safer, but your best bet is always to walk and avoid your car.
Just do the walking.
Just do the walking, yeah, as much as you can.
Yes.
But it's not practical for some people. They just live too far away from the university to do it.
Yeah, okay. Another question from Jimmy Fannin. How does the known amount of available raw material, for example, rare earth metals, compare to the amount we would need to make enough solar panels and batteries such that solar would be the primary energy source?
I don't know those numbers. Batteries are particularly a challenge, I think, because of the cobalt. It's not so much the lithium. Wind energy, there are some rare earth metals whose names I can't even pronounce, which are used in the permanent magnets, which are a real issue for the wind turbines. You know, a lot of these systems do use precious metals. And so the idea is that we continue to evolve these systems so that we don't need to use those materials. I guess that's, you know, to the best that we can. And that's certainly the goal of a lot of research, is to avoid using precious metals. But I'll ask everybody else, what's the number one most used material on the planet? This one's easy, it's water. What's the second most used material on the planet? Sand. And some people say we're already running out of sand. So Jimmy's thinking about those rare earth metals, but you know, for putting up buildings, there can be a scarcity of sand because it may not be where it's needed to make that building. So even sand could become too scarce.
Okay, I see Alexandra raised her hand.
She's saying concrete, not cement. I might have meant cement.
There you go.
Yes, of course.
Of course. I try not to do that, but you know,
Been
I'm old, Alexandra. You know, my brain doesn't work as intended. It doesn't always cooperate with my voice.
I was just thinking it's probably exhausting to give a talk like this at the end of the day, but for everybody's interest, I do have to say that the second most widely used material is concrete. And to all the questions coming back about efficiency of the construction, yes, we could replace the binders, but if they will not last, then the net gain on the carbon dioxide reduction is not going to be achieved. So second most widely material in the world after water. Thanks, Bruce. This was fun.
Thank you, Alexandra.
We have more questions, but Bruce, I want to check with you. Do you?
Yeah,
want to
I think, you know, I
continue?
mean, I personally, I think an hour and 15 minutes is the limit anybody should be subjected to. So, you know, we have classes that are an hour and 15 minutes. We do that all the time, but an hour and a half, I don't know. So, you know, I'd be happy to answer anybody's questions if they want to send them to me. My email is blogan@psu.edu. And for those of you who might want slides, feel free to contact me as well.
I will also copy everything on the chat and send to you. So whoever,
that'd be great. Thank
yes, the other, you know, leftover question haven't been answered, you can take a look.
All right.
Okay. Thank you, everyone. Just say it out loud again. The recorded video will be on CE event. So come back and check if you don't receive an email from me. But I will try to figure out how to, email all the registrants and send the link. Yeah. Thank you, everyone. Have a good
Thank you
evening.
for listening.
Yeah. Bye.
Get solar panels.
And walking.
An excellent talk. Thank you so much.
Thanks.
Thank you, Bruce.
Thank you. So
That's
thanks,
great
Lily,
talk.
for organizing it. And it was a great opportunity to be able to share this information to people. I think it's so important. So
It's great. Yeah. Everyone should know this and do something within themselves, power capacity. Yeah.
yep, I agree with the point that, some of this is beyond our control, but we have more power than we think. So
Bruce, so
collectively we can use that.
there's just a handful of people left. So I was just thinking, would you consider recording this talk as a giveaway for people to do in classes? When we talk about material science in 336, the whole sustainability concept translated to all the aspects. So while I can play this talk for them, there were quizzes that probably won't show up, but if you had a deliverable for like undergraduates, so many people could present it. Just like the first person said, have a drink and just watch, but spreading the knowledge, right? And this is such an important concept to talk about.
Yeah. So Alexandra, what I'm trying to do is I've decided to experiment on college freshmen. And so I'm doing a freshman seminar where, the talks are maybe 15, 20 minutes or something like that. They're really short on each of the subjects, and those will be recorded and I can share those. But I can easily share my slides, and you can just push those slides right into your course however you want. I mean, I have a lot more slides obviously than I shared today. And
if you give permission to, I will just present the seminar because you discuss them so much better than any of us will try, and there's so much knowledge that went into creating these slides. So this will be one of my lectures in 336.
Yeah.
It's a great conversation. Why are we actually figuring out the numbers behind anything we talk about? Super cool. Great seminar, Lily. Well,
thank you, Alexandra.
It was a great seminar, Bruce. Not
Thank
me.
you
Thank you, Bruce.
Thanks.
Great.
Okay, I'll go
Really
now.
appreciate it. Yeah.
Bye now.
Bye.